Learning target for the next lesson is calculating geometric probabilities, and I will show you 3 different settings where we'll do that. The first setting where we'll use this, an example, would be, it looks like a number line. This could simulate something like, say, a bus schedule. And say the time between buses that, I've got 1, 2, 3, 4, 5, 6, 7, 8. And each of those spaces could be 1 minute, 2 minutes, 5 minutes. It doesn't matter. But say they're 2 minutes. Okay. So every 16 minutes, a bus or a train comes by the stop. It stops for 2 minutes, stops for one of those time segments, and lets people get on and off. Well, the blue event here, while the bus is stopped, what would be the probability that somebody would show up at the right time there? Well, the person could get there any time during this stop, and these are all the times when the bus is not sitting there waiting for people. Well, there's a total of 8, so we've got 8 chances is our total, and the person could end up, the time that they arrive at the stop could be any dot along this line, but the chance of it being in that spot would be 1 because it covers that one entire time slot. And so that's the amount of time that the bus or the train would be at that stop. So it would be 1 out of 8 would be the geometric probability for that. And that comes out to 0.125 or 12.5% if we were to calculate it as a percentage. Well, let's say that this stops at a stadium or an airport or something, and they need much more time to load and unload, and that's represented by this space here. How many spaces or how many time slots does that cover? It covers 1, 2, 3, 3 slots. So the chance of a person showing up while the bus or the train was waiting at that stop would be 3 possibilities out of the total before another cycle starts and another train would come, and the total is 8. So 3 out of 8 is the probability that a person, when they show up at that stop, would be able to get right onto the bus. And 3 over 8 comes out to 0.375 or 37.5%. So it's the geometric probability of something on what would look like a number line. Our second look at geometric probability is in a pie chart. And we just got finished working with pie charts. And you know that we had to draw the central angle for the pie chart, and we figured out how many degrees there were. And in here, all we're going to do is kind of backwards engineer that. We're going to look at, okay, we've got so many degrees. What fraction of the circle is that? And we've actually done some problems similar to this before. So let's say this is like a spinner in a game, and they're not evenly spread. Obviously, 5, you'd have a better chance of getting a 5 because it has 120 degrees and is bigger than all the rest. And getting a 6 is the smallest. So what would be the probability of, let's say, spinning a 1? Well, there's a total of 60 degrees, and a whole circle is 360. So we want to figure what's the probability, and if we reduce this, we would end up with one out of 6 or 0.16 repeating. So as a percentage, it would be 16% or 17%. As a fraction, 1 in 6 chance. So the geometric probability is 1/6 or 0.16 repeating. Well, how about spinning a 3? That's got 45 degrees. Well, 45 out of 360 And when we work that out, we get an eighth, which is 0.125. So 12.5%, or 1/8, 1 in 8 chance. So geometric probability works out similar to others. It's just what's the chance of getting what you want out of all the possibilities. The last example is actually created with the composite figures that we've worked on already. And in this case, we've got two shapes. And what two shapes do we have here? We've got a square and a circle. And we've got to figure out the area of each of those. And the shaded area just has these corners. So what are we going to do with those two shapes to find the shaded in area? Well, the way we had to work these before is we've got a square with the not shaded area cut out of it. So we're going to take the square, subtract off the circle. And when we had things that were added on to the outside, we added some pieces together. Here we're subtracting one out. So we're going to find the square and subtract the circle. The area of the square, this is the center of the circle, so we've got 8 inches there. So the entire diameter would be 16, which is the same as the side of the square. So we've got 16 squared, which is 256. The circle is pi times the radius squared, and I'm going to round that off to the nearest whole number, so it's 201. When we subtract those, we've got 55. So the total area of the shaded space is 55. Divide that by the total possible, which is the entire outside of the square. So we've got by 256. And the decimal we get for that is 0.2148, and it keeps on going. So we could round that off to 0.21, or a 21% chance of throwing a penny or a dart, whatever, and something landing in that space. The kind of situation where this might be used is like the carnival games where you throw something and see if it lands in the space. Shuffleboard. You can also use geometric probability in 3D space. Scientists use that to figure out what's the chance that a particle or an atom or some random insect or something would be in a certain space in whatever it is that they might be studying. So we can figure out the percent chance of something being somewhere. It doesn't mean that it will be there, but that's our chances of that event occurring.